Hey guys, this is Professor Janacek. Want to talk about power series, want to specifically go over derivatives and integrals of power series. So let's begin with the basic power series. Let's let f of x be the sum as k goes from 0 to infinity of c sub k times x minus a to the k. And let's name the radius of convergence for this r, make sure that's a positive value. Now, a power series written as a function is simply an infinite polynomial function. So I can treat this like a polynomial function, meaning when I take the first derivative, I'll use the power rule. I'll take that exponent, multiply it in the front as a coefficient, and then subtract 1 there to make a new exponent. The second derivative, I do the same thing. Multiply by the exponent in the front and subtract 1 from the exponent in the back. So that's exactly what we've seen before. Nothing really new. It works just like a polynomial function. One thing I do want you to notice is that our original function started at 0. When we take the first derivative of that, though, remember my first term is a constant. When we take the derivative of a constant, we get 0. So we can actually start our first derivative at 1. The second derivative, similarly, we can begin that at 2 because the first two terms would go to 0. Make sure that makes sense to you. Now, for an integral, if we want to integrate f of x, again, we treat it like a polynomial. This is an indefinite integral, so we will have that arbitrary constant. We usually put that in the back, but I'm going to write it in the front so it doesn't get confused with my summation. And to integrate, we'll simply add 1 to the exponent and then divide by that new exponent value. Just like a polynomial function, nothing really unusual about this. What's nice about these is that, remember the radius of convergence for my original function is r, so turns out the radius of convergence for the derivatives and integrals also that same value of r. So once you find the radius of convergence for one of these, you've got the radius of convergence for all of them. Pretty nice. Now let's take a look at an example. Suppose we have the function f of x is equal to the sum as k goes from 0 to infinity of x to the k over k. Before we look at derivatives or integrals, let's see if we can remember what the center is. This one's centered at 0, and the coefficients. The coefficients have the form 1 over k. Make sure you remember those vocabulary words: the center of the power series, the coefficients of the power series. All right, let's take a look at the first derivative of this. Remember, the first term would be a constant. The derivative of that constant is 0, so I can actually begin this summation at 1. And then we're going to use our power rule. Now, I do have that coefficient there in front. Let's not forget about that. I'm going to write that down first so I don't have to worry about losing it later. Then the power rule, we're going to multiply by k and then x to the k minus 1. We can simplify this a bit. 1 over k times k gives us just 1, so we end up with the sum as k goes from 1 to infinity of x to the k minus 1. And ta-da, there is our first derivative. However, I want you to notice that we can actually adjust this summation a bit. If I start this summation at 0, then my terms would have the form x to the k. So I could sum k going from 0 to infinity of x to the k. It might be a little easier to work with. Let's now take a look at the integral of this power series. Let's integrate f of x dx. Again, for integration, that's an indefinite integral. I do need that arbitrary constant. Let's go ahead and write that down in front so I don't lose it later. And now for the series, I'm going to start again like I did before. I'm going to simply write down my coefficients so I don't lose that. Now remember, we're looking at f of x. We're not integrating f prime, we're integrating f. All right, so integration, we'll take x, raise it now to the k plus 1, and then divide by that k plus 1. Typical polynomial integration, nothing too crazy. I can simplify this just a wee bit. 1 over k in the front, divided by k plus 1 there in the denominator. I'll rewrite this as the sum as k goes from 0 to infinity of x to the k plus 1 over k times k plus 1. Now you could distribute that k in the denominator. That's up to you. I'll leave it there for now. But not too bad, I hope. Let's take a look at the next example. Let's see if we could find the power series representation of the inverse tangent of x centered at 0. So to begin with, our function is the inverse tangent of x. Of course, if you want to write that as arctangent, that's fine. Now, this first step is a little bit tricky. You'll have to recognize this as an integral. We are talking about integrals today, right? So this is the integral of 1 over 1 plus x squared dx. Now, you might be familiar with this the other direction. If you have the integral of this, then you end up with the inverse tangent. I'm using this in the reverse of what we typically see this in, but you should be able to recognize it nonetheless. Now, this next part is also a wee bit tricky, so hang in there. Let's see if this makes sense. This is a geometric series, believe it or not. Now, if you don't believe me, let me remind you what the geometric series looks like. It's the sum as k goes from 0 to infinity of a r to the k, and it is equal to a over 1 minus r as long as the absolute value of r is less than 1. In this case, I see that 1 over 1 plus x squared looks a lot like a over 1 minus r. That's how I recognized it as geometric. So I'm actually going to start with the right-hand side of this and go in the reverse direction yet again. In this case, my a value is 1, and the r value, be careful with this, it's negative x squared. Which means, again, I have this part, and so I want to rewrite it in terms of that series. So we can write this as the integral, that's still there, of the sum as k goes from 0 to infinity of a, which is 1, I don't really need to write that, times r, negative x squared to the k. And of course, our differential there in the back. Let's see, I can go ahead and simplify this or rewrite this just a bit to make it an easier series to work with. Let's write this as negative 1 to the k, and then x squared to the k is x to the 2k. Okay, let's see. Now, if we integrate this, again, I'm looking at integrating this bit right there, treating that as my polynomial function. We end up with our constant c plus the sum as k goes from 0 to infinity. I'll keep that negative 1 to the k in the front. The x will add 1 to that exponent and then divide by that same exponent. All right, well, there we go. There is one way of writing our function, but I want you to notice something. Since we know that the inverse tangent of 0 is equal to 0, meaning that when we put in a 0 for x, we get 0 as the result, then we could say that 0 is equal to, notice I'm going to use this right here. I'm just going to replace the x with 0. So we get c plus the sum as k goes from 0 to infinity of negative 1 to the k times 0 to the 2k plus 1 over 2k plus 1. But 0 raised to the power is 0 times stuff divided by something other than 0. All of that's still 0. Adding a whole bunch of those up together, we still get 0. So this whole thing is 0. But look at this. Oh, wait, hold on, that's not 0. This whole thing is 0, so that gives me c plus 0, which is just c. So here we go. C is equal to 0. So that means I can rewrite this function, f of x is equal to, instead of c, I know that is 0, so I don't need to write it. The sum as k goes from 0 to infinity of -1 to the k times x to the 2k plus 1 over 2k plus 1. And there we go. Power series representation of the inverse tangent of x. Pretty nice. Not so bad, I hope. Enjoy!